Previously we defined a function delta of x which exists in a big way at a point in space. In fact, it has infinite impact at a point, and let us call that point x equal to 0, which we define as the origin of the x-axis, and it has no presence elsewhere. That is, points other than x equal to 0 do not care to know about it. In the language of physics, we represent the situation by drawing an infinite spike at x equal to 0, and we have described the function delta of x by writing it down explicitly in mathematical terms, clearly mentioning that at x not equal to 0 it is 0, no presence of it whatsoever, but at x equal to 0 it has infinite dominance, that is, it shows an overwhelming presence. But if we stop its description here, we would miss the main feature of the function we are referring to. The physically tangible effect that this function has is that the area underneath it, or in other words, the area it stands upon, is a constant, and we chose that constant to be unity for our convenience. We normalized it or set the standard in that way. We in this video study some properties of the Dirac delta function that we defined, and now we agree to face some problems based upon the properties we describe. Let us start with this integral over f of x Dirac delta of x dx, and the integration is from minus infinity to plus infinity. That is, the entire x-axis is under our scanner. Recall the definition of Dirac delta function. Multiply both sides by f of x, and hence on the left we have f of x into Dirac delta of x. Look at the right hand side. It is f of x into 0, and the product is 0 for x not equal to 0. And it is f of x into infinity, the product being obviously infinity for x equal to 0. Now let us multiply the Dirac delta function by f of 0. The left hand side is f of 0 into Dirac delta of x, and the right hand side is f of 0 into 0, the product being 0 for x not equal to 0, and it is f of 0 into infinity, resulting in infinity for x equal to 0. Clear that the right hand sides are equal. So the product of f of 0 into Dirac delta of x is the same as the product of f of x into Dirac delta of x, and look at the right hand side, it is 0 for x not equal to 0 and infinity for x equal to 0. Let us consider now the given integral. We find that f of x Dirac delta of x occurs as integrand. Obviously, we can replace it by f of 0 into Dirac delta of x. Now, f of 0 is a fixed value or number and can be safely pushed out, that is shunted out of the integral sign. So we are left with f of 0 into integration over the entire x-axis, the integrand now being Dirac delta of x dx, and its value is unity as the Dirac delta encloses unit area. So the answer to the given integral is f of 0. Let us enclose the result we have got just now in a green box. It is a very popular expression and widely applied. We now discuss this result. Let us point out the essential features that one needs to remember while using it in solving problems. In other words, let us underscore when we can apply this very popular, simple but elegant relation. Let us ask the question, why does 0 appear as an argument of f in the right hand side? What is the origin of the 0 you see within f on the right hand side? In fact, the Dirac delta of x occurring in the integrand is actually Dirac delta about x equal to 0, and let us write it explicitly. So now you can see where from the 0 appears. Put in another way, we have to write the argument of f as the coordinate of the point around which the Dirac delta sitting within the integrand is defined. In other words, the 0 gets shifted as shown. Now another point, we have to be sure that this point 0 around which Dirac delta is defined lies within the range of integration. Only then we have f of 0 as the result, because only then the Dirac delta contributes, that is, presents unit area that it holds underneath. Obviously, it follows that the right hand side would be 0 if the integration range forgets to include this point about which Dirac delta is defined, because Dirac delta is 0 at all other points. We make another very important observation. You see that x, which is the integration variable, occurs linearly as the argument of Dirac delta function. So we have to check these points before applying this very popular and most used integral. Aren't we feeling sufficiently emboldened to expand our territory? We feel we can. Let us make a slight variation of the same integration. That is, let us now take the Dirac delta sitting within the integration sign to be defined about, say, x equal to a. What will its value be? Previously it was defined around x equal to 0. Let us recall the result we derived. If integral carries Dirac delta of x minus 0, then the result is f of 0. Accordingly, if the integral carries Dirac delta of x minus a, then the result would be f of a. So we have got the result. Let us put it within a green box. Let us now evaluate this integral, which is virtually the same as the previous integrations. You see that the integrand has f of x into Dirac delta of x minus x0 dx. The difference is in the limit. It is from a to b. It is not specified whether x0 lies within a and b. So you get two answers, and they are as follows. If x0 is within the integration limits a and b, then the value of the integration is f of x0, as the Dirac delta is defined around x0. But if on the other hand the x0 lies outside the integration limits, then the value would be 0. In fact, Dirac delta is valued and respected only at the point x equal to x0. And if you are elsewhere, you won't be able to see its influence, and Dirac delta has no meaning for you then. We have derived and discussed a property of Dirac delta function. The two slides, one on your left and the other on your right, shows some properties. We shall apply these formulae and solve certain problems involving Dirac delta function. So this is our first challenge. You can see 4 options on the right hand side. It is a multiple choice type question. Let us not be bothered in any way whatsoever about the choices or the options, because we would solve the problem straight away in a formal manner and get the answer. If any of the choices given are correct, we would accept it. Consider the integral written separately. Let us investigate the limits and check if the point around which Dirac delta is defined finds a place within the limits. The Dirac delta is defined or constructed around the point x equal to 1 and the limits are 0 and 3. Obviously, x equal to 1 falls within the prescribed range of integration, that is 0 to 3. Also, the argument of Dirac delta function is linear in x. Let us use this formula that we derived. The answer is therefore x square evaluated at x equal to 1 and the value turns out to be 1. So we have solved the problem. The next problem, and let us do it. Here we see that the point x equal to 2 around which Dirac delta is defined sits within the range of integration 1 to 3 and the argument of the Dirac delta is linear in x. We can apply the same formula as depicted in the slide within the green box and the answer is x cubed evaluated at x equal to 2, which turns out to be 2 cubed, that is 8. So we have solved the problem. This is another problem which is of similar type and can be done as we did previously. The answer is worked out for you to check. This slide also shows a similar problem inviting your scrutiny. Let us now turn to another problem. Let us do it and find out if it is also on the expected line. The argument of Dirac delta is linear in x, which is the integration variable. The limits within which we have to perform integration is 0 and 3. But the point about which Dirac delta is defined is x equal to minus 1 and we see that it remains outside the limits. It is an excluded point and Dirac delta has significance only at the excluded point x equal to minus 1, the point which is left out. Clearly, as the contributing point is excluded from the range of integration, the value of the integral will be 0. In fact, this is the formula we will use. Therefore, the value of the integral is 0. And we have found the correct answer sitting in the first option amongst the 4 given options. This slide shows similar type of problems. Please work them out for yourself and check the correctness of the workouts in the slide that you are viewing currently. Similar for this slide also, 2 questions and their answers have been worked out. Take your time and see if the workouts are okay. We next move over to describe another property of the Dirac delta function. Let us evaluate the value of the Dirac delta of kx and the Dirac delta of minus kx, where the quantity k is different from 0. Let us consider the integral minus infinity to plus infinity, the integrand being f of x Dirac delta of kx dx. Let us enclose it in the red box. We put y for kx with the aim of shifting from variable x to the new variable y. The relations between x and y have been shown and that between dx and dy evaluated. Now make these substitutions in the original integral. Take 1 by k outside the integral and now use the formula we derived as shown in the green box. Using this formula we get the value of the integral in the red box to be f of 0 divided by k, and let us embed it in a blue box. Let us write the result we have got separately. Let us focus on the quantity f of 0 enclosed in the green box. We now use the same formula as indicated to get the integral in the green box. We are thus in a position to compare the two integrals, one in the red box and the other in the green box. Note that 1 by k has been pushed inside the integral. Comparison yields the result we were in wait for, namely Dirac delta of kx is Dirac delta of x divided by k, and of course k is not 0, for then the right hand side is undefined, it would blow up to infinity. We quote the essential results in this slide. Let us move on, since we now wish to evaluate the Dirac delta of minus kx with k non-zero. Proceeding as we did previously, let us consider the integral within the red box and change the variable from x to y by substituting minus kx for y, and then use the same formula shown in the green box to get f of 0 by k as depicted in the red box down under. This slide shows what we have got so far. And now let us make use of the same formula to substitute f of 0 by the integral shown in the green box. Taking the k within the integral, we rewrite the two integrals, having derived the latter from the former, they being equal. Comparison gives the following. Dirac delta of minus kx is equal to Dirac delta of x divided by k, where k is not 0. In this slide, we summarize the results that we got. In fact, we have derived them, and they are very important relations that are referred to over and over again. Let us now combine the relations as shown, and the last result embedded in the blue box can be rewritten as Dirac delta of modulus k into x equal to the Dirac delta of x divided by modulus of k. Let us enclose it in a green box. This result is of paramount importance. This slide, as you can find, has picked up the result we derived just now. Let us put k equal to 1 so that we end up with the following. Dirac delta of x is equal to the Dirac delta of minus x. In other words, the minus or the plus has no effect externally. I mean, the value of Dirac delta function is same whether it is minus x or plus x in the argument of Dirac delta. Such type of function which refuses to give importance to the minus sign in its argument is referred to as even function. So Dirac delta function is an even function, since a change of its argument by a negative sign does not impact it, does not change its value. Dirac delta of x minus a and Dirac delta of a minus x both have same value. The even character of the delta function leads to the following equality of integrals. Just check and satisfy yourself. It is my experience that we often get confused while trying to write down the argument of f? Would it be f of x or would it be f of x prime? Let me clarify this. In this integral, the integration is over x, as evident from the term dx. So after integration, we would not discover any x. So the answer would be f of x prime. And we are not bothered about whether we have delta of x minus x prime or x prime minus x. So comes the second result. And here you notice that the integration is over x prime and not over x. So after performing integration, we would never find x prime. What we would get is x. And we are not at all concerned whether Dirac delta has preferred to keep its argument x prime minus x or the other way around, that is x minus x prime. We showed that Dirac delta is an even function. Can we prove the same from the unit area property of Dirac delta? The question you see in the slide asks us to check if the two properties, namely unit area of Dirac delta and the property that Dirac delta is an even function, are consistent with each other. Let us write down mathematically that area which Dirac delta rides upon is unity, and let us change the variable from x to minus of y. So dx is minus dy and the limits get inverted, and we end up with, as you can see, the integral that involves Dirac delta of minus y. Obviously the integration variable is y. You should appreciate the fact that there is no harm if we change the name of the variable y. Call henceforth the variable y as x, and hence we get the integral shown in the green box, and it is equal to the integral sitting pretty in the violet box, which in fact is the integral we started our discussion with. Let us pick them up and write in a new slide afresh. And here it is. Comparison gives the property we earlier derived, that is Dirac delta is an even function. And this is another property, a generalization of the previous result. Let us now employ these properties to solve some problems. We have collected the properties that we derived. Dirac delta of x is Dirac delta of minus x. This signifies that there is no harm if we add or push a negative sign in the argument of Dirac delta function. This is another property, a generalization of the previous result. And here we have shown the value of Dirac delta of kx or minus kx, and it is Dirac delta of x by k, and of course k is non-zero. Let us consider this example, and we would apply the formula as written in the slide within the red rectangle. It gives a rather simplified expression of half into Dirac delta of sin x minus 1 by root 2. Now let us take up a multiple choice question. We focus our attention on the argument of Dirac delta, and it is 3x plus 1. So let us take help of the formula shown in the red box, and we get Dirac delta of x plus 1/3 with 1 by 3 coming out. With this we have the integral as shown, and we see that it involves Dirac delta of x plus 1/3. We note that the argument is linear in x. We also see that minus 1/3 lies within the limits of integration minus 1 to plus 1, and so let us use the formula as shown in the green box to get the result 1 by 27. So we have solved the problem. The third option is what we accept as true. We wish to address another similar type of problem, and here it is. Using the formula as shown in the red rectangle, we can make the argument of Dirac delta look more friendly. It is t minus 3 at the cost of a half outside. After ensuring that the argument of Dirac delta is linear in t and that t equal to 3 falls within the range of integration 0 to 6, we can evaluate the value of the integrand at t equal to 3, and the answer is 9 by 2. So the problem is solved. This slide shows a similar problem, and to solve it we have to run on the same track. Verify the workout.